Hi everyone, my name is Sonia Valeria-Sacoto. Thank you for attending this virtual conference. Today I will present a research that has been conducted jointly with Professor Wade Cook, Professor David Güemes Castorena, and Professor Joe Zhu. The title is Evaluating Efficiency in Non-Homogeneous Environment. In the next slide, I will present you the context of this study. Briefly, I will explain what was the problem that we were tackling in this research. The conventional DEA methodology evaluates the relative efficiency of a set of comparable DEMUs. When all DEMUs use the same inputs, produce the same outputs, experience the same operating conditions, and generally operate in similar environments. In many applications, however, it can occur that DEMUs fall into different groups or categories where the efficiency score for any given group may be significantly different from those of another group. In such settings, one group of DEMUs can have advantage over those DEMUs in another group. Consider, for example, the case of bank branches falling into two groups, namely those with a wealthy customer base, the rich branches with significant investment in mutual funds, mortgage, etc., and the remaining branches that cater to poorer customers who purchase few financial services products. In such setting, if investment constitutes one of the outputs of the branches, then one might expect that the majority of efficient DEMUs will come from the group of rich branches, while the most poorer branches will be declared as inefficient, possible very inefficient. The recommended projections for poor branches may be unattainable, in that they can only reach the frontier by becoming rich branches. Consider as well the example that we are presented in this study. The case of economic activities in Mexico is one of these. In that setting, certain industry groupings perform a significantly different manner than is in other groups. In the next slide, I will present briefly the case of Mexico, the economic activities. The DEMUs under study are a set of economic activities in Mexico. These economic activities are organized under the North American Industry Classification System, well known as NAICS codes, allowing one to form groups of similar economic entities. The evaluation of performance of these activities is based upon parameters obtained from the economic census recorded by the Instituto Nacional de Estadística y Geografía, INEGI. The data of this analysis is collected every 5 years. Unlike the case where DEMUs constitute a rather homogeneous set, like hospitals operating in similar settings, it happens that when one performs a conventional DA analysis on the entire set of activities, the average DA scores for them are substantially different from one another. As a result, one might argue that those DEMUs in the best performing group are in a more favorable position to achieve efficient status than is true of the DEMUs in the other groups. Therefore, the set of DEMUs might be seen as being non-homogeneous, especially because they do different things. Some produce primary products, while others provide welfare services for the inhabitants of the country. Some economic activities hold a significant advantage in relation to others because they can produce more due to the technology or to advanced and specialized processes. Thus, it will be necessary to adapt the conventional DA methodology so that the similar DEMUs can be compared on an equal footing. In the next slide, we have a question that raises this research. So the question here is how to evaluate a large number of units which may not be directly comparable. In the next slide, I am presenting first what is the data envelopment analysis, just to briefly explain how is the traditional DA. Data envelopment analysis evaluates the performance of different entities where success cannot be measured by a single factor such as profit. This technique has been applied to a variety of efficiency evaluation problems, where managers wish to conduct a performance evaluation and analyze the decision alternatives. It measures the performance of decision-making units in relation to other similar DEMUs. DA creates an efficient frontier where the best performing units from the dataset are located. The other units not lying on the efficient frontier are said to be inefficient. DA provides a measure of the amount by which units will need to change to become efficient through radial projections to the frontier. What it is interesting yet challenging about this study is that it involves the comparison of DEMUs, in this case economic activities, that in most respects are not directly comparable. High technology industry compared to farming, for example. The next slide, I am briefly explaining the problem that we are tackling here. Generally, DA is applied to DEMUs operating in the same environment, meaning that they constitute a homogeneous set. For example, see the case in the left-hand side where universities are compared in university. In such a situation, efficiency scores and accompanying projections to the best practice frontier should be realistic portrayal of the technical efficiency standing of each DEMU. This should mean that targets or projections are relatively achievable. However, the study herein involves situations where the DEMUs fall into what might be seen as different groups. In such settings, one group of DEMUs can have advantage over those DEMUs in another group. The next slide. So the starting point of this research is the choice of the appropriate variables considered as an inputs and outputs for the performance evaluation of each economic activity in a region. The variables considered are, for instance, we have used labor or total employee people, salaries, gross fixed capital, total fixed assets, and for the outputs, we have included total gross production and gross added value. Now, detailed discussion on how some of these variables are defined will not be discussed here, but rather are available in the literature. In the next slide, I am explaining the traditional VRS model. Due to the wide variety of size of economic activities, that in this case are the DEMUs, we employ the VRS technology and examine the efficiency from the perspective of the output orientation. The result obtained will be illustrated in a two-dimensional chart with the input on the horizontal axis and the output on the vertical axis. Furthermore, and since we are using the output orientation, it is easy to recognize that there are some DEMUs that use much more inputs to produce a given level of output than is true of other DEMUs. This leads to the idea that there are some advantage and some disadvantage groups of DEMUs. In the following figure, we divide the set of DEMUs into three groups, where those in pink represent the advantage DOMs, which are close to the frontier, those in blue the disadvantaged, and those in green the most disadvantaged group. The next slide. When we are running the traditional VRS for the problem herein, it can be claimed that the advantage or disadvantage characterizing DEMUs in one group versus another group might reasonably be based on the average efficiency for those two groups. We view it statistically one might offer the hypothesis that the two groups of the mu's are not drawn from the same population. The question then arises as to what should be done to give a fair chance to both or all groups of the mu's, in the sense that the average score for the groups will display a greater degree of similarity, hence being seen as operating on a level playing field. One way of making for a more level playing field is to compensate disadvantaged mu's. In the next slide, I would like to use to demonstrate a table that we have been divided the groups of the economic activities, and we have used a terminology that, for example, we have three groups, N1, N2, N3 for the economic activities. In this case, where N3 will be named as the most disadvantaged group, N2 the second most disadvantaged, and N1 the most advantaged. We point out here that efficiency measure phi greater than equal 1, hence the mu's with lowest scores are close on average to the frontier. The next slide, I am presenting early works that have been done comparing different groups. For example, in the study by Banker and Murray, considering our case of the mu groups N1, N2, and 3, their categorical variable approach will see N3 mu's evaluated only against other N3 mu's, N2 mu's against all units in N2 and N3, and finally, N1 mu's evaluate against the mu's in all three sets. In our current setting, however, we wish to create an environment where all the mu's are evaluated against one another as a single group. The study of Seaford and Xu, it is demonstrated that one can obtain multiple frontiers against which to evaluate the mu's. Specifically, one first runs the DAM model and obtains a frontier. The fishing units derived are then removed from the set of the mu's, and the model is run again with the reduced set, leading to a second level frontier, which is again removed from the set, and so on. The process terminates when no mu's are left to be evaluated. The purpose of having the multiple frontier is to be able to compare any given mu against multiple peers, leading to measure of attractiveness and progress for that mu. In our setting, however, our purpose is to obtain an objective measure of the extent to which one subset of the mu's is advantaged or disadvantaged as compared to another subset, and then use that measure to adjust the disadvantage set, such as to create a favored context within which to measure technical efficiency. In the next slide, I would like to present the previous model or the original model and our new methodology. So what should be done to give a chance to all groups of the mu, in the sense that the average score for the groups will display a greater degree of similarity, is the question. So hence, here we are looking at operating on a level playing field. As well, it would be hoped that some efficient mu's will come from each of the groups, and for inefficient branches, for example, frontier projections will reasonably achievable. We propose the idea that to facilitate a more fair evaluation, there is a need to compensate disadvantaged mu's. To formalize the compensation concept, let's assume that the mu's can be divided into two identifiable groups, namely an advantage group N1 and a disadvantage group N2. For a disadvantaged mu, we argue that only a fraction of that mu input will be needed to generate its output if it did not find itself in a disadvantage. In other words, we might claim that a portion 1 minus alpha of is dedicated to coping with an accommodating environment. Here, alpha is treated as a decision variable lying in a prescribed range 8 to 1. Let us refer to 8 as the reduction parameter. This problem will then be solved for each DMUs. The idea here is to adjust, reduce, in other words, inputs of the DMUs n in 2, so as to push the DMUs closer to the frontier, and in the process, hopefully, bring the average efficiency score for N2 closer to that of N1. A problem with this model is that once an adjusted DMU hits the frontier, further adjustment then pushes the frontier up, meaning that the DMU in N1 can become less efficient. At the same time, efficiency improvement for inefficient DMUs in N2 may not materialize even with input reduction, as such reduction is happened to peer DMUs at the same rate, especially those that have already reached the frontier and are moving that frontier up. As a result, the model playing field that is in your right-hand side is unlikely to bring about the desired fair and level playing field. In the next slide, we can see that one way of moving the average efficiency of DMUs in N2 closer to that one on N1 is to fix the frontier generated by the solution of the original model. In other words, undertake the adjustment to DMUs while requiring that those adjusting units remain within the production possibility sets generated by the original model. In that regard, let J denote the set of efficient units generated by the original model. We point out that some members of both N1 and N2 may appear in J. Now, for each inefficient DMU, consider problem, the model that is in the right-hand side. Here, constraint 4 define the PPS, the production possibility set, for the overall DA model given by the original model, which is in your left-hand side. At the same time, whatever reduction in inputs occurs, the resulting adjusted DMU should lie within that possible production possible set, as expressed by restriction number 3. In the next slide, we can see that clearly the model that is at your left is not linear by the virtue of the fact that alpha is a decision variable. The usual change of the variable technique of Charnes and Cooper in 1962 is applied. The reduction parameter A provides a raw measure of the level compensation afforded each inefficient DMU in a disadvantaged group. It generally coincides with the proportions of inputs going toward the main task of the DMU, namely the production of the outputs. The remainder is directed to the task of coping with the unfavorable environment in which the DMUs find itself. One might postulate as well that a reasonable measure of compensation is simply the difference between the efficiency score arising from original model and the new model. However, the scores may not be directly comparable, given that they arise from different projections. That being said, it is therefore pertinent to develop a more formal measure of compensation in the form of an efficiency score. In other words, we wish to evaluate the relative degree of compensation not only in terms of the reduction parameter A, but as well in terms of the quantities of aggregate inputs diverted away from the production of that DMU's outputs. To formalize this idea, we argue that the disadvantaged DMU is in two lines of business. In the next slide, I will show you that still there is a problem with this situation. Now, it is possible that for the chosen value of the parameter A, the mu J0 may not only project onto the frontier, but as well may push the frontier up. To address this, we suggest to replace one of the constraints. as you can see in this slide. Here, we have imposed an epsilon value. This epsilon value is a small positive number which permits to be adjusted arbitrarily close to the frontier without touching it, hence without distorting it. In the next slide, I show you the second problem. The second problem says that for the chosen parameter A, one or more of the adjusted components of xi, namely alpha I times xi, may hit the frontier or bump against the epsilon in the objective function before the last constraint becomes binding. Therefore, it's suggested to be modify the objective function to the following. As you can see here, we have included the epsilon and we have imposed that in the objective function. Next slide. Okay. The reduction parameter A provides a rough measure of the level of compensation afforded each inefficient mu J naught in a disadvantaged group. It generally consists with the proportion alpha I of inputs xi going toward the main task of the mu, namely the production of the outputs. In this study, we wish to evaluate the relative degree of compensation not only in terms of the reduction parameter A, but as well in terms of the quantity of aggregate inputs diverted away from the production of that mu output. To formalize this idea, we argue that disadvantaged mu is in two lines of dim. Its primary business is that this cares about, namely the generation of outputs, while its secondary lines of business is the requirement or responsibility it assumes in coping with an accommodating environment. The next slide. Here are some of the results that we have obtained from the previous studies when we were evaluating the set of economic activities in Mexico. As we can see in the second row, it shows the original values by using the original values that we obtained from the original BRS model. Now, when we are using the new model and by using different values of A and using this model, it is possible to find a good approach. So we can get very similar values for the average efficiency group in the three groups that we divided the entire set of economic activities. Next slide. Well, here I will present the conclusions of this paper. So this paper examines the problem of applying DA in what can be seen as non-homogeneous environments. The setting for this is often one where the demus fall into distinct groups, wherein the average performance of one group is significantly different from that of another group. In some circumstances, grouping may be well defined by size, technology type, demographics, and so on, while in others, there may not be obvious explanation for observed difference in performance. Here, we look specifically at a set of economic activities in Mexico and make the observation that when activities are grouped into industry codes, vastly different average efficiency score arise, while there is no convenient single-dimensional explanation for such large discrepancies. It is clear that the usual homogeneity that characterizes most DA application is not present in this very heterogeneous environment. This observation has prompted the development of a new DA methodology that attempts to compensate this advantage group of the muse relative to a base advantage group. The next slide. The model developed here can be regarded as a mechanism for separating a demuse for technical efficiency from a score that is partially explainable by environmental inequities or imbalances. The methodology constructs for each member of a disadvantaged group two measures. The first of the measures via the new model is intended to capture a fair evaluation of the demuse technical efficiency. It accomplishes this by undertaking a reduction of that unit's inputs with the purpose being to bring it to a point where it can be fairly compared to other advantage DMUs. The second measure provides a compensation score that describes the extent to which the DMUs has been disadvantaged. The ideas presented here can potentially lend important insights into the performance of business activities over the time. One of the models used to look at time series data is that based on the Malmquist index. Using compensation methodology together with the Malmquist indexes, a more realistic portrayal of concepts like frontier shifts may be captured. This is subject to future research. The next slide. Thank you very much for your attention. If you have any question regarding this presentation, please do not hesitate to contact me by this email. I really appreciate your time. Thank you very much.